Okay, let's dive in. Today we're exploring something that honestly affects how you interact with almost everything man-made. Your keyboard, your car seat, even the handle on your fridge.
Right, we're talking about ergonomics,
Mm.
or you might hear it called human factors engineering. Same thing, really.
And defining it simply.
It's the study, basically, of how people interact with their working environment. The tools, the machines, the space itself, even how information gets shown to them.
So the big mission here, and this is key for our deep dive, isn't just about being comfy, is it?
No, not at all. It's about using what we know about human abilities and, importantly, human limitations to design things, the goal. Better performance, better safety, better health, and just making it easier and more satisfying for you, the person using it.
It's interesting you mentioned limitations because this field really got a huge push during World War II, didn't it? High stakes.
Oh, absolutely. Think about aviation back then. Systems were getting incredibly complex, incredibly fast. If a pilot couldn't read a dial correctly or couldn't reach a critical lever in time, well, the consequences were dire. They had to figure out how to make the cockpit fit the pilot, not the other way around.
That makes a lot of sense. And today, it's not just fighter jets. We see the need everywhere, especially with the rise of things like cumulative trauma disorders.
Exactly. Those injuries from doing the same motion over and over or holding awkward positions for too long. Think assembly lines, but also think about sitting at a desk all day. It's a massive issue in modern workplaces, both industrial and office settings.
Which leads us, I guess, right into the core philosophy of the whole field.
It does. And it sounds almost too simple, but it's fundamental. Design the job to fit the person.
Not make the person try to fit the job.
Precisely. Stop forcing people into unnatural positions or making them adapt to confusing controls. The design itself has to account for how humans actually are.
Which connects to that great saying, work smart, not hard.
Our sources really hammer this home. Real gains in productivity, and especially safety, come from changing the way work is done, making it smarter, reducing the chance for errors, not just yelling at people to go faster in a system that's basically set up to fail them.
Okay, so if we're designing around the person, that raises the question, what should people be doing versus machines?
Yeah, that's a critical distinction. Humans, we're actually amazing at spotting subtle signals, like picking out a faint warning light on a busy dashboard. We're good at inductive reasoning, figuring things out from patterns, and crucially, handling the unexpected. The curveballs machines just can't anticipate.
Right, and machines.
Machines excel where we falter. High-speed, repetitive tasks. Perfect for a machine, storing and recalling tons of data instantly. No problem. Applying consistent heavy force. Easy. Good system design leverages both strengths.
And this seems like a huge but.
It is. The massive complication is, all people are not alike. You can't design for some mythical average person because they don't really exist.
We vary so much.
Hugely. Size, strength, reach, eyesight, flexibility. The range is enormous. So design has to account for that variability.
Okay, so how do we actually manage that range? That brings us to anthropometry.
Exactly. Anthropometry is just the science of measuring the human body specifically for design purposes, taking those variations and turning them into useful data.
And there are different kinds of measurements, right?
Yeah. Broadly, two types. You've got static measurements. These are when the body's in a fixed position, like your height standing straight or the length of your forearm. Simple dimensions.
And the other type.
Functional, or sometimes called dynamic measurements. These are about movement. How far can you comfortably reach forward while seated? What's the range of motion in your wrist? Things related to actually doing a task.
Okay, got the data. How does the designer actually use it? Like for an office chair?
Well, for something like a chair, or maybe a driver's seat in a car, the gold standard is designed for adjustability. If it can be made adjustable, it probably should be. Let the user fine-tune it to fit them.
Makes sense. But what about things you can't adjust? Like, say, the height of a doorway, or maybe a safety railing?
Right. For those non-adjustable things, you have to design for extremes. This is where percentiles come in.
Percentiles? Like on growth charts?
Kind of, yeah. You use data from the largest potential users, typically the 95th percentile male, to figure out minimum clearances. Like, how high does that doorway need to be so almost everyone can pass through without ducking?
Okay, so that's for fitting through. What about reaching things?
For reach, you design for the other extreme. The smallest users, typically the 5th percentile female, you set the maximum distance for critical controls like an emergency stop button based on their comfortable reach. That way you ensure pretty much everyone can operate it safely.
And I suppose you need the right data for your specific users, too.
Well, absolutely. That's the target population principle.
Yeah.
Generic data is okay sometimes, but if you're designing, say, equipment specifically for firefighters, you need anthropometric data for firefighters who might have different builds or be wearing bulky gear compared to the general office population.
Got it. So that covers the physical dimensions. But what about the body as an engine? How much work can people actually do? Let's talk work physiology and biomechanics.
Right. Work physiology looks at how the body generates energy. Mostly it's aerobic, using oxygen. But for intense bursts, it can switch to anaerobic, which doesn't need oxygen immediately, but builds up lactic acid.
And this idea of oxygen debt.
Yeah, when you start working hard, your body uses energy faster than you can supply oxygen.
Yeah.
You go into this debt that you have to repay later during recovery by breathing heavily.
Okay, interesting biology, but why does an engineer designing, say, a conveyor belt system need to know about my oxygen debt?
Because it directly impacts workload assessment and safety. Knowing the energy demands of a task helps determine how long someone can safely do it, especially in hot environments. It dictates things like mandatory rest periods or tells you if you need specialized gear like cooled vests to prevent heat stress. It literally sets the limits for strenuous work.
Wow, okay, so physiology sets the endurance limits. What about preventing immediate injury, like strains and sprains? That's biomechanics.
Precisely. Biomechanics applies principles of physics forces, levers, motion directly to the human body during tasks.
Mm.
It's all about preventing those cumulative trauma disorders we mentioned earlier and also sudden injuries.
So what are biomechanics experts looking for when they analyze a job?
They're hunting for key risk factors. The big four are usually high forces lifting something too heavy, extreme joint positions like bending your wrist way back repeatedly, awkward or static postures, holding your arm up for a long time, and highly repetitive motions. Any of those, especially in combination, is a red flag.
And if they find them?
The job needs a redesign. Either change the tool, change the workstation layout, introduce mechanical aids, or alter the procedure itself to eliminate or reduce that risk factor. You engineer the hazard out.
Okay, let's shift from the body itself to how the person and the machine talk to each other, the interface.
It's a people-machine interface. Yeah, it's a constant loop. The machine gives information through displays.
Like gauges or screens.
Exactly. The human operator sees or hears that, processes it, decides what to do, and then uses controls, buttons, levers, keyboards.
Which then tells the machine what to do next. And the loop continues.
That's the cycle. So designing that interface well is critical. Let's start with displays, mainly visual ones. They tend to fall into categories based on what they do.
Okay.
You've got quantitative displays. These give you a specific number. Think a digital speedometer in your car or a temperature readout.
Just the facts.
Pretty much. Then there are qualitative displays. These show a status or trend like hot, cold, full empty, or in the green zone. The needle on an old-school fuel gauge is a classic example. You get the condition quickly without needing the exact number.
And the third type.
Representational. These are more pictorial or symbolic. Think of icons on your computer screen or a weather map. They represent something else. The goal for all of them is clarity and speed. Can you understand it quickly and accurately?
There's even like a formula for how big letters need to be on a sign depending on how far away you are.
Yeah. Yep, there is. H equals 0.00022 times D plus K1 plus K2. It factors in viewing distance, D, and conditions like lighting. It gets quite specific to ensure readability.
So when do we ditch the visuals and use sound instead? Alarms, maybe?
Exactly. Auditory display sounds are better in certain situations. When the message is simple, short, and needs immediate attention, like a fire alarm, urgency is key.
Or maybe if your eyes are busy.
That too. If the visual system is overloaded, or if the person needs to be looking somewhere else, an auditory signal can cut through. Also good if the message doesn't need to be referred back to later.
Okay, makes sense. And now the other side of the loop, the controls. You mentioned earlier that one concept is super important here.
Ah, yes. Compatibility. This is absolutely fundamental.
Compatibility with what?
With human expectation.
Oh.
What we expect a control to do based on its design, location, or how it moves, we often call these ingrained expectations population stereotypes.
Like turning a knob clockwise usually means more or increase. Volume, temperature.
Exactly like that. Or flicking a light switch up means on in some places, down in others. That's a stereotype, even if it varies geographically. Red usually means stop or danger. Green means go or safe. These are deeply learned.
And when you violate that expectation,
That's where errors happen, sometimes catastrophic ones. The source material had a really stark example, a control lever on a machine. Pushing it forward should have moved the machine's table forward, following the spatial stereotype, but it was wired backward. Pushing forward moved the table up.
oh, wow.
Yeah. The operator, under pressure, reverted to instinct, pushed forward, expecting forward movement, and caused a major error because the table moved unpredictably up. Lack of compatibility invites mistakes.
So it's assuming you get the compatibility right, what kinds of controls are there?
Well, you can group them. Discrete controls have fixed positions. Think a three-way light switch or a car's gear shifter, park, reverse, neutral, drive.
Got it. And the other kind?
Continuous controls. These allow settings anywhere within a range. A steering wheel, a dimmer switch for lights, a volume knob.
And for any control, really, you have to worry about someone hitting it by accident, right? Especially critical ones.
Oh, definitely. Preventing accidental activation is a huge part of safe design. Engineers use several tricks.
Like what?
Well, you can recess buttons so they're flush with or below the panel surface, harder to hit accidentally, or put guards or physical barriers around them. Think of the cover over a fire missile button in movies,
Yeah.
or actual covers on critical switches in real life. Sometimes they require two actions, like lifting a cover then flipping the switch, or interlocking controls, where you have to operate one thing before another becomes active, maybe requiring a longer push or a specific sequence.
Lots of thought goes into just one button. Okay, let's zoom out now. Take all these ideas, measurements, displays, controls, and think about laying out a whole workspace. There are principles for that too.
Yes, four main ones often guide workstation layout, trying to make it intuitive and efficient.
Okay, what's the first?
Importance. The most critical controls and displays, maybe the main power switch, emergency stop, primary readouts, need to be in the prime location. Right in front, easy to see, easy to reach, without thinking.
Makes sense. Number two.
Frequency of use. Things you use all the time should be close by, easy to grab. The things you only use occasionally can be a bit further away. Don't make someone constantly reach awkwardly for their main tool.
Got it. Third.
Functional grouping. Group controls and displays that relate to the same function or system together. Like all the climate controls in a car are usually clustered. It helps you build a mental map.
And the last one?
Sequence of use. If you typically perform tasks in a specific order, arrange the controls or components related to those tasks in that same sequence, left to right or top to bottom. It guides the workflow.
Okay, that's layout logic. What about just the height of, say, a workbench or a desk?
The general rule there, whether you're standing or sitting, is to keep your forearms roughly horizontal and your upper arms hanging naturally vertical. This minimizes muscle strain, especially that static fatigue you get from just holding a position.
And if you are sitting, the chair becomes pretty important.
Oh, hugely. A good ergonomic chair isn't a luxury. It's essential. It needs to be stable, usually meaning 5 casters on the base, not 4. It absolutely must be adjustable. Seat height, seat depth, if possible. And good lumbar support for your lower back is crucial. If you have to lean forward to feel the backrest, it's not doing its job.
This sounds especially critical for people working at computers all day, VDT workstations.
Absolutely. Visual display terminals. Bad setup there is a recipe for eye strain, neck pain, back pain, wrist problems, all those musculoskeletal issues. You need the adjustable chair, sure, but also the right monitor height, top of the screen, usually at or slightly below eye level. Keyboard positioning is key too, to keep wrists straight. And managing glare on the screen is often overlooked but vital.
And one more thing about layout, making sure someone can actually fix the equipment later.
Maintainability, yes. Often forgotten in the initial design phase. Can a technician actually reach the components that need servicing? Is there enough space to work? Are parts clearly labeled? Good ergonomic design considers the entire life cycle, including maintenance.
Right. Now, we've talked a lot about fitting the job to the person, but it's important to remember which people we're talking about, right? It's not just one type of worker anymore.
That's a critical point as we wrap up. The workforce is changing. Designs have to accommodate that reality. More women are in jobs that were traditionally male-dominated, requiring tools and equipment suitable for a wider range of strengths and sizes.
And the workforce is aging.
Exactly. An aging population might have different vision requirements, maybe reduced strength or flexibility. Designs need to account for that. And crucially, we need to design for individuals with disabilities.
And this isn't just a nice to have, is it? There are legal requirements now.
Absolutely. Laws, like the Americans with Disabilities Act in the U.S. and similar legislation elsewhere, mandate accessibility. Workplaces must make reasonable accommodations. Equipment needs to be usable. You can't discriminate in employment because your facility or tools aren't designed inclusively.
So ergonomics becomes tied into equity and legal compliance too.
It's fundamental to it.
Okay, so bringing this all together, our deep dive shows that ergonomics, or human factors, is really about moving away from just expecting people to adapt, often badly, to their tools and environment.
Right. It's about embedding intelligence and understanding of human capabilities and limitations into the design of pretty much everything, from how much force it takes to push a button, to the height of your desk, to the color of a warning light.
It's optimizing that constant conversation, that feedback loop between us and the things we use.
That's a great way to put it. It's less about isolated tasks and more about the continuous interaction between human capabilities and the designed environment.
So here's a thought to leave folks with. If so much of good design relies on compatibility, on those population stereotypes, the things we just expect, like clockwise means more, what happens with brand new technologies, things where there are no established stereotypes yet. Think about controlling things with hand gestures in VR or AR.
Ooh, that is the frontier, isn't it? We're literally watching new stereotypes form right now. How do you make a gesture for open file or zoom in feel intuitive when there's no real-world physical knob or button it mimics?
And how long does it take for a completely new interaction, maybe some complex hand wave in virtual reality, to become so ingrained in the next generation that it feels just as natural and obvious to them as turning a doorknob feels to us today?
Exactly. That process, figuring out the right way to interact with the unfamiliar and then having it become the expected standard, that's where ergonomic design is heading, making the new feel inevitable.